Hello. In this video, I'll be discussing about whether a retaining wall can be designed in ETABS program using the reinforcing method, or in other words, can we design a retaining wall applying a pier section? There is a misconception to some of our engineers that ETABS does not design walls for out-of-plane bending moment, which is actually not correct. ETABS designs a wall for both in-plane and out-of-plane bending moments. The design problem that we have here has a dimension along the length. It is 24 feet long and the height is 12. And on the wall we have applied a lateral load under the live load pattern equals 300 pounds per square feet in the y direction, which is the out of plane for the respective wall. So if you look at the y direction, you can see that the y direction is the out of plane direction for the retaining wall. If we analyze the wall or the model and then look at the deflected shape under the live load pattern, then we will see the deflected pattern, how it is deflecting. So the deflected shape is quite logical. That's how it was supposed to deflect. And if we look at the bending moment that we have, the bending moment can be checked in two different ways. One is under the shell forces. For example, D wall 2, we can check for the M11, M22. There are several ways of checking it. For example, if we switch on the local axis of shell, then we can understand which axis is 1, which axis is 2. The red one is 1, which is along the wall, and the green one is the 2. Basically, we'll be checking the 2, M22 bending moment. The bending moment should be 0 at the top. That's what we see here, 0, and it will increase gradually, and it's increasing gradually. And at the bottom, it is about 34 or maybe 35, exactly 35, 35. Okay. Since we have a and what load combination we are checking it under? The load combination is D1, which is 1.2 dead load, 1.6 live load. So 1.6 live is actually working here. So the length of the wall is, as I have already said, that it is 24 feet. So 35 multiplied by 24 gives you 840 kip-ft. Okay. The bending moment here is actually a little bit lower. However, we can take average 35 kip-ft per feet length, and then if we multiply this with the total length, then we will get the pier force, pier bending moment. So let us check out the pier bending moment, how much it is. The wall 2 moment 2 will be the out of plane bending moment, and we turn or click on this, activate this pier tick here, and then you will see the bending moment for the D wall 2 is 829, which is correct actually. The moment I calculated was 840, and I had seen that there was some low bending moment at the edges. So this one is the actual bending moment, total bending moment for the entire wall. Now let us design it applying the uniform reinforcing method. Just select the wall and then apply uniform reinforcing. Then 4000 PSI concrete number 5 bar, spacing 6, clear cover is 1.5, end bar is also 5, number 5, actually 16 mm rebar. The reinforcement to be checked, it is to be ticked here so that we can get the demand capacity ratio. And here similarly I am preparing an Excel which I can prepare for single reinforced or maybe double reinforced as I like. So let's say there's insert the data here is 4 KSI, the FY is 60 KSI. So how can we show that the FY is 60 KSI? We can find the rebar grade from here. You can see that the rebar material is A615 grade 60, which specified, so which indicates that it is a grade 6 river. So yes, moral loss of elasticity of at least 29,000 ksi is known to us. Width is 12. Width actually, we are dealing with the whole length of the wall, which is 24 feet. 24 into 12 is 28 inches. Depth of the wall or the section is 15 inches. 15 inches is the thickness. Okay, then the width is inserted. The depth or thickness of the wall is 15 inches, which you can see here. I have defined the wall as 15 inches thick with 4000 psi concrete. So let us put here 15. Clear cover, as I had showed you for the wall fire, it was 1.5 inches. Let us put here 1.5 inches. Then top reinforcement area and bottom reinforcement area. So here it is actually a beam analysis is done here for the wall. So the ones who have already designed retaining wall or sliding beam already understand this concept. So let us determine how much reinforcement we have already provided to the retaining wall here. The amount of reinforcement we have provided by specifying number 5 river at the rate of 6 inches in the center is this 31 square inches. So in 31 square inches, there are two curtains like this. There are two curtains. One curtain is this, and the other curtain is this. Okay. So basically, we can say that if we reverse this is the bending moment you can see, and this is the maximum bending moment. It is 830 kip-ft or 829 kip-ft for the D wall to load combination. Now, if we let's say if we rotate it, then it will be a beam, right? Rather than a wall, we can analyze it as a beam. Okay, yeah, that works. There's a beam here now. There is a cantilever beam. We have top river, we have bottom river. So how much is the top river? It will be half of the 31 inches. And how much will be the bottom river? It will be again the half of the 31 inches. So which reinforcement is basically working here? This is the top reinforcement or the reinforcement, this reinforcement, right? Okay, this reinforcement is responsible for resisting the bending moment. However, since we are doing the double reinforcement analysis, we need to put both the top and bottom reinforcements. So the top reinforcement is 15.5 square inches, which is 50% of the 31 square inches. Bottom reinforcement is also 15.5 square inches. Top reinforcement center, right? We have to determine it. It will be 15 depth minus clear cover minus rebar dia divided by 2. Diameter of the bar is a 16 mm rebar, so 6.625 is the diameter inches, right? Divided by 2. So we are at the center of the rebar now. So this is it. Top reinforcement centroid D dash is from top, so we don't need this. Sorry, we have to add this all. Okay, make it plus. Okay, let's do it again. The clear cover plus river dart. That's it. 125. Top first reinforcement row centroid. This is the same since there is only one row of river at each party. Bottom reinforcement centroid will be 15 minus this actually. So this one is correct. Yeah. So what is the bending capacity? We have to solve the equation here. The value is 0, and for C we will be solving the equation. It will be 0. T minus C equals 0. Also we will be solving this equation. Both these equations are the same actually. Is reinforcement is same, so the bending capacity will be also same. So how much bending capacity do we have here? Here's 903 kip-ft. Okay, from the beam analysis we get the bending capacity as 903 kip-ft. So the capacity is that is the capacity 903 kip-ft. And then we need to write the applied bending moment. Applied moment is basically, we had already checked it out from this, is 829.44. 829.44. So the demand capacity ratio should be applied moment divided by capacity, which should give us a value of 92%. Now, if we design this wall for the same reinforcement that we had chosen here, okay, and then if we check the fire demand capacity ratio, the ratio is 89%, which is very close to this manually calculated 92%, and can be said that it is okay. The difference is only 89%, right? 89% and 92%. So 89%, the difference. What is the deviation, or what is the percentage of difference here? Okay, divided by, say, this one is the let's take the base. The difference is only 3%, which may be deemed acceptable. Therefore, we can say that the ETABS program designs retaining walls for out of plane bending moment, and we don't really use ETABS program for designing retaining walls, but in some complex structures, we have basement walls which work as both a shear wall and a retaining wall. So in that case, there is an interaction of out of plane bending moment and in plane bending moment, and also the axial load. So a question frequently arises whether the out of plane loads that we have applied, are these really accounted for in the design of the structural member or the structural wall? The question is answered here that yeah, the out of plane bending moment is covered by ETABS program. So that was a main topic of this video. Thanks for watching.